So I want to jump directly to, the Dinkin diagrams and the roots and weights, which is very relevant for you. The context of this lecture are, I'll be talking about roots and weights, about the rank of a Lie algebra, the commutation relations in the Cartan basis. I'll give as an example the SU2 and the SU3 algebra and how the Gelman matrices that we talked yesterday, what role do they fit in. I will talk about, the Viol reflections associated with the roots of your lattice, the Viol group, about the classification of the semi-simple Lie algebras. In reality, the classifications really was done for complex Lie algebras. We'll talk a little bit about the difference between real, complex, and quaternionic. We'll talk a little bit about the exceptional Lie algebras, about the Dinkin diagrams and root spaces. And then at the very end, I briefly will mention the Mckay correspondence, that you probably know more about that than I do, because Fang is very familiar. Remember a few years ago Yeah. And anyway, the Mckay correspondence really has to do with the solutions with diophantic equations. How do you pronounce in English? Diophantic equation? Diophantine equation. Yes. So in reality, that's where it all comes from.
What about that? The W-I-L, is that a Viol or is that a whale?
Viol. Hermann Viol.
It's
German. German. Yeah. He was wild. He was wild. Okay. So let me proceed. So essentially, the whole purpose of how Cartan came with this idea is that, the simple roots associated with a given Lie algebra have a very important property, is that they can reproduce entire algebra with giving you the minimum amount of information. For example, let's suppose that we wanted to study the SU2 group and the SU2-10 algebra. So imagine, if you take 10, if you square it, you get 100. If you take 1, you get 99. It has 99 generators. Imagine all the possible combinations that you could have. Combining all the commutations relations, you'll have a very large number of combinatorial relations. However, the SU10 has rank 9, so you can actually deduce the entire algebra based on only 9 simple roots. So the 9 simple roots in this case will be like the basic building blocks of your entire SU10 algebra with 99 generators. And you could encode everything by knowing the properties of your 9 simple roots. So with those simple roots, you can actually reconstruct the entire tree. Imagine you have a tree made of 99 branches. So out of the 9 fundamental roots, you can generate the whole thing. So it was highly non-trivial. And of course, those mathematicians, Lie Cartan was really a very wonderful mathematician, right? Not because he was French, but he was very good. So essentially, the bottom line is that the roots and weights associated with Lie algebras is a very deep construction that allows you to reproduce your whole algebra by giving you just the basic minimum amount of information. That's the whole point of the lecture, really. Okay, so what do I mean the Cartan basis? You see, when you have a Lie algebra, you can break the generators in such a way. Of course, you have to be very clever in choosing the right basis. Okay? So by Cartan basis, it means that you have a given number of generators that can be diagonalized simultaneously. So these generators define what is called the Cartan subalgebra. And imagine you have a matrices. So you have as many matrices as the rank of your Lie algebra. So H are really your generators of your Cartan subalgebra. And the index I ranges between 1, 2, and the rank of your Lie algebra. For example, when you look at the SU2 algebra of rotations, it has rank number 1, only rank 1. We'll go through it. When you look at the exceptional E8 algebra, it has rank 8. It means it has 8 Cartan generators. Okay? So out of the 248 generators of your exceptional E8 algebra, 8 of them belong to the Cartan subalgebra, and the remaining 240 form part of what you call the 240 roots that you are familiar with. For example, when you look at the exceptional group G2, which is the automorphism group of the autonomions, the G2 has 14 generators, but that number 2 tells you what the rank is. G2 means that the rank of your algebra is 2. So you have 14 generators, 2 of them belong to the Cartan subalgebra, and the remaining 12 belong to the roots. Okay? So this will also explain why you have the notation that mathematicians use. So the remaining generators outside the Cartan subalgebra can be paired such that to every generator you can associate a mirror generator. It's like taking a reflection with respect to a mirror. So to a given generator, you associate the mirror reflection. Okay, so remember that I talked yesterday and also the day before that there are many ways you can label the generators of a Cartan algebra. You can label them by giving numbers, 1, 2, 3, 4, whatever. Or you can use a double index notation. Remember when I talk about rotations? I said that you could have a rotation with about the 1, 2 plane, the 1, 3 plane, the 3, 5 plane. Okay, that's another way I can label the generators, because I find the geometrical interpretation of my algebra. So if knowing the geometrical interpretation will allow me to label the generators, it's like a bookkeeping device. So in the Cartan, when he discovered this, he realized that the way you index your generators, the generators are going to be indexed by a set of numbers. And those set of numbers can be all regrouped as the coordinates of a vector. Okay? So when I mean alpha here, really, the majority of books do not write the arrow here. They just remove the arrow and they assume people know that by alpha it means a vector. Another way of saying it is that we'll see later that these alphas are related to the eigenvalues associated with these Cartan matrices. Okay, so the bottom line is that
so the generators which are in the Cartan subalgebra are the simple roots?
No. The simple roots lie outside. Okay. The Cartan generators think of it as a bunch of diagonal matrices, in a very pedestrian way. So the diagonal matrices commute with each other. So essentially think of it as the diagonal matrices.
These are the Cartan matrices, right?
No. The Cartan is something else. The Cartan matrix of your Lie algebra is something else. Okay?
So the generator matrix of Cartan algebra are not the Cartan?
No. Okay, so by the rank, let's talk about the rank of a Lie algebra. You see, all the information of a Lie algebra can be encoded in the root space whose dimension is the rank of the Lie algebra. For example, E8 has 8 Cartan generators, so the rank of the Lie algebra is 8. So you construct your root lattice in an 8-dimensional space. For example, when you look at the SU2, which is the algebra, of the Pauli spin matrices, has rank number 1, so you only need a 1-dimensional space. Okay? If you look, for example, as G2, G2 has rank 2, so you only need a 2-dimensional space. Okay?
E8 has rank of 8, but it also has this dimension of
248. Yes, so you're going to draw 240 vectors that live inside that 8-dimensional space. Okay? Those vectors are not linearly independent. No, those vectors will be linearly dependent.
Yeah,
okay? Yeah, of course, you will have a fundamental basis made out of 8 vectors, which will, in that case, will be...
simple roots.
Yes. The simple roots will be 8, and out of those simple roots, by performing linear combinations, you will be able to generate the remaining 240 roots. Yeah, 240 minus 8. Okay. Remember, 8 of the dimension of your space corresponds to the number of Cartan generators. Okay?
The dimension of the group depends on what?
No, the dimension of your space where you build your root lattice depends on the number of Cartan generators. So E8.
Cartan generators are correlated to the simple root.
No, to the rank of the algebra. The rank of the algebra.
The rank of the algebra does equal to the number of.
Yes, also, we'll talk about that. Yes, yes. It turns out that the rank of the algebra also equals the number of simple positive roots. Okay, simple positive roots. Okay. So, so the root space will be endowed with an Euclidean metric. Remember, with a positive definite metric, which should not confuse it with a Cartan-Killing metric. Remember yesterday I talked about the Cartan-Killing metric? Do not confuse the Cartan-Killing metric with the metric that I put in your root space. You see, your root space is going to be an Euclidean space. Okay? So E8, for example, lives in 8 dimensions, 8 Euclidean dimensions. Okay. So will we see that the non-zero vectors, the roots in this space, obey this relationship? It's like taking the inner product of one root vector with the other, and you normalize, essentially by divided by the length square of one of the root vectors. So this essentially is like taking the dot product, for example, of and normalizing by the length square of one of the roots. Okay, we'll see later why you have these two. And remember, this inner product can take a bunch of positive values or negative values. Remember, these are the non-zero vectors, the roots. I'm talking about not only the simple roots, but all the roots of your space. Okay, so you have a bunch of roots. Out of those roots, you have a subspace made out of simple roots. The simple roots will allow you to reproduce all the other roots. But by roots, here I mean all my roots. Okay? So you can take the inner product among pairs, and it will be constrained to be, that inner product will be constrained by these integers. It could lie between minus n and m, where n and m are integers. Okay, so essentially the classification of Lie algebras is connected to in how many ways can we classify these inner products. Okay, so the bottom line is that this inner product multiplied by 2 lies between minus n and m, where they're integers. Okay, so let's go to the nitty-gritty now. Let's look at the canonical commutation relationship in the Cartan basis. Okay, so let's suppose that I have a Lie algebra of a given rank, and the rank so I have a bunch of Cartan generators where I and j label the number of Cartan generators. Well, you can represent them as matrices. Yes, I'll give you an example in the next slides where you can represent all of these objects by matrices. I will give you an explicit example.
But for Cartan algebra, is there any other representation?
Oh, you can represent it in terms of matrices, or remember we talked about the possibility of representing them by differential operators also. But think of them as matrices. So I have a bunch of matrices. Remember, the number of commuting matrices gives me the rank of my algebra. The number of commuting generators. And then I'm going to have a bunch of non-commuting generators that, okay, so now I can write. Yeah.
Bold H.
Yes, that's what I'm going to tell you. Bold H, in my case, is like having a vector whose entries are labeled by the Cartan generators. Okay, so I'm going to explain very clear what H bar is. Okay, so remember that I have. Can you see that again? Let's suppose I have one Cartan generator. I have another one. I have another one. 3. Okay, until the rank of your Lie algebra. What name do you want to give to the rank of the Lie algebra that I mentioned? N, little n? Yes. Okay, little n, okay. So what happens is this collection of generators I can rewrite them as if they were the entries of a vector in an n-dimensional space. Okay, so this is what I mean by boldface. Okay, essentially is the set of Cartan generators, and I can represent them as if they were living in an n-dimensional space. Okay. Now, because these generators are commuting, okay, imagine, well, the eigenvalues will be 0, but this is what I mean by boldface. Okay, what do I mean by, okay, and then you're going to have the remaining generators of your algebra. Okay, I'm going to label them by vectors. Okay, Amrik. So I have vector number 1. Okay. Vector number 2, okay, and vector is going to have a certain number. Let's call it capital J, okay? You'll see why I call it capital J. Now, the Viol reflection is going to mirror these vectors. By Viol reflection, of course, I mean reflect. Okay, we'll talk about that. So you're going to have the conjugate root, if you want to call it, will have the label will be the opposite of vector number 1. Then you have the other label, the opposite of vector number 2, and you have another label which is the opposite of vector number J. Okay. So I'm going to add the total number of generators. Okay, I'm going to have n generators here. I have j here. Okay, and then I have j here, right? So the total number of generators will be n, which is the dimension of your Lie algebra, plus twice j. That must be equal to the dimension of my Lie algebra. Okay? So n is the rank, the dimension of your Cartan subalgebra, and because the roots will be paired in mirror conjugates of each other, that's how I get 2 plus j. Okay. Let's. Which group do you want to play with? Do you want to play with the E8 or the G2? Which one would you like to play with, for example? E8. Okay. Yeah. E8 has rank 8, right? Okay. So E8 has rank 8. Now the dimension of my algebra is what? 248, right? Okay. So what do I need to have here? 240, right? 240 root, and there are pairs in multiples of 120. Okay, so I have 120. The Viol reflection is another 120. That makes 240 plus 8 is 248. Okay, it's this. Anyway, you have my notes. Okay, so this is what I mean. Okay, so what do I mean when I write? Okay, let's suppose now I have the Cartan generator. So number 1, if I want to take the commutation relation with a given root, okay? Okay, let's suppose I have, okay, I write vectors here just to emphasize that they are vectors. Let's suppose that you have root label j, for example. You want label j, for example. So what you're going to have here is like Ray said, these roots will be eigenvalues associated with matrix number 1. So I'm going to have an eigenvalue associated with my root j. And because remember, this little j here labels the root. The root is a vector. So because a vector has many components, I need to specify which component I'm talking about. Here I have label number 1, right? So then I need to specify here the first component because it's associated with the first Cartan generator. And here I have a multiple of my root here. Okay, and remember, I'm not using the Einstein summation convention.
Can you?
Yeah. So let me just go back to it.
What have you written there?
Yeah. Here,
In the parentheses?
in the parentheses, I put here to remind you that this is the first component associated with root number j. Okay? Why do I have the first component here? Because I'm taking the commutator with the first element of my Cartan subalgebra. It's just an index bookkeeping device. Okay?
So that alpha I hi here on
Yeah.
the third line
Yeah.
is not an Einstein summation.
No. You see, no, it's
So
not.
what does that mean?
No, okay, this is what I'm writing now. Okay, let's suppose I repeat this equation. Can you see from there, again?
Yeah.
Okay, let's repeat this with Cartan generator number 2. Okay?
That's a Cartan generator.
Yeah.
Or that's a Cartan basis.
No, Cartan generator, the first Cartan generator. Okay, in my Cartan basis, of course. This is my first Cartan generator. Let's go to Cartan generator number 2. Okay? Then I take a commutator with my root vector number j. Okay, this is the j root vector. Okay, and then if I take the commutator, so what I'm going to get? I'm going to get an eigenvalue. These are eigenvalues. Okay, and I make an eigenvalue associated with my root j. Okay. Okay, so I'll let that. Yeah.
So
Yeah.
E alpha j is the generator
Yeah.
corresponding to the jth root? Or
Yes.
how am I
Yes.
supposed to
Yes.
do this?
Yes. The
What does it look like? The E is also a matrix, right?
yes. We'll spell because I have to start slowly and then build up in crescendo. You know. So I have a generator. How do I label that generator? By an index, and that index is a vector. It's a collection of numbers, right? So this means generator. This is the j root, and this is the generator associated with my j root. Okay. So E is my generator associated with the j root. Okay. Yeah, this notation is very important because most of the books, they remove the vector symbol and they don't write indices or sub-indices. They just write everything in very compact notation. So you need to unravel what the compact notation is. Okay, so here, because I have Cartan generator number 2, okay, here I have really, this is a vector. So I'm taking, because this is Cartan generator number 2, I'm taking the second component of my vector. This is what this 2 means, okay? And this is an eigenvalue, so then I just multiply times my root.
So the alpha j, why can't you just use a j instead of alpha j? Because alpha j seems to be just like alpha 1, alpha 2, alpha 3, alpha 4.
Yeah.
To the alpha j.
Because I want to use alpha j because all of the books in group theory use alpha for roots.
So the alpha also is related to the roots, right?
Alpha is one of the roots.
Yeah.
Alpha 1, alpha 2, alpha 3, alpha 4 are the roots.
Yeah.
Okay. But
He wants to write alpha j because if he wrote j,
Yeah.
then what would he write for the eigenvalue? He would have to write alpha j because alpha j2, which is the eigenvalue.
Yeah.
J is not the eigenvalue.
yeah.
Eigenvalue of
Yeah.
the-
So he wants to be consistent.
Yes, I want to be consistent. Yeah.
But the E is the roots, so then I don't understand
E is the
why.
generator.
Capital E is the generator associated to alpha, which is a root.
Okay, so it's a generator associated to a
Yeah.
root.
Yes.
And he hasn't told us how the construction of the generator in terms of the alpha is.
Not yet. Yes. Okay, so then you repeat this, you complete this with the other components of your Cartan generators, right? So remember, you told me to use the letter N for the rank of the Lie algebra. Then okay, then I'm going to the last one. Okay. So I have my generator, I'm sorry, my generator associated with root number j. Okay, so I'm going to have an eigenvalue here times my root and I have my generator associated with the root number j. I have my root is here, and then I need to give you which component, because the roots are vectors. I have an n here, so I have to tell you that this is the nth component associated with this root vector.
So these eigenvalues, which are alphas,
Yeah.
components of alphas, are your structure constants.
In that will be, yeah, in that case will be the structure constants associated with this commutation relations, yeah.
Commutation.
Yes.
So how does the H related to E?
H is completely separate of E.
So
Separate. H is just your diagonal matrices, and the E's are the off-diagonal matrices. Think about it, okay? Think about that, yeah. Okay, and the alphas really are just eigenvalues, you know, eigenvalues. Okay, what happened
Why is it true?
Yeah.
Why is it true
Yeah.
that these commutation relations hold? Why is that an eigen?
No, but this is how you define it. Because Cartan wanted to classify the algebras. Then you have to go through a very elaborate procedure to see, you have to impose the Jacobi identities, and you have to impose constraints among the inner products and see how many possible inner products you can have. And knowing how many possible inner products you can have will allow him to classify all the algebras. Okay? This has to do with the Cartan matrix associated with the algebra. But that comes later. That comes later.
No, but you wrote down the commutation relations. I'm wondering where did you get that from?
Yeah. No, this is what Cartan did to start his classification program.
Where did Cartan get that from?
Yes. Because he was very smart. He was very smart, you know.
So it was like Ramanujan dreaming.
Yes. He was very, very smart, you know. Essentially, yeah. No. Essentially, he wanted to find to find a basis. You see, remember, your Lie algebra is a vector space. So he wanted to find a basis that simplifies everything to the maximum.
But is it a principle then that
Yeah.
for any two given a pair of diagonal and off-diagonal matrices,
Yeah.
which happen to be generators of any Lie algebra,
Yeah.
will have this commutation relation? Is it
Yeah. I guess
it always work?
it will always work. It will always work. Yeah. So now because I have H1 here, H2 here, and Hn, what happens is that you can collect everything symbolically. You know, you can collect everything symbolically by having this boldface notation here. I have H1, H2, H3. So then I can gather everything, and in simplifying notation, I can write boldface here. I have my generator associated with root number j. Okay, and now I collect all my components of my eigenvalues, right? This is component number 1, component number 2, component number 3, component number n. Remember, now I'm going to collect all these h's, h1, h2, into a boldface h, you know. So here I'm going to collect my first component, second component, n component. And this is what one means by alpha vector, okay, E alpha. Because now a vector is made out of components, 1, 2, 3, n components, okay? Because
Is it a dot?
No, there is no dot. So what happens is that, of course, because there is no summation convention, okay, because there is no summation convention, what people do is they remove the label j, they remove the label j, they remove the label j. you know, and also they remove the, you know, in many cases the alpha. Did I include it there? Well, I left it there to simplify, okay?
So this is really like 8 equations.
Huh?
This is really 8 equations or n equations.
Yes, exactly. Yeah.
No, but is that product between the alpha vector and E a pairwise product?
No. It's just this is eigenvalue number 1, eigenvalue number 2, eigenvalue number 3 for n. And then what happens here, I have this bold face. This is just a symbolic way of writing.
It's more like a tensor product by
Yeah.
8-dimensional.
Yes. Okay, so you could actually This is very.
That to me looks like a pair. It's not a pairwise.
Tensor product of you put things.
Yeah.
You have 8 equations and you write it vectorially as a.
No, but the right hand
equation
side.
is
Right hand side, I don't understand how it's a tensor.
No, it's not a tensor. Well, I guess you could call it a tensor product. It's just I can order. Okay, you see how I order my H into H1, H2, right? So I can have root number J, right? I can order it. Okay.
Yeah, I get that.
Yeah. Yes. Okay.
But when you multiply that with E,
Yeah.
I don't understand what
What it means this. This equation means 8 equations. That's what it means in condensed notation. Okay? Yeah, I know this is not very easy at the beginning, you know. But okay, so essentially this equation, what it means, it translates into 8 different equations. You know, remember when we wrote the Newtonian equation of motions, you can write them in components form, or you can write them in vectorial form, right? So this is, okay. Now let's look at the second commutation relation, okay? The second commutation relation, okay? And Rick, here you're really going to have an Einstein summation convention. Here you're going to sum over all indices. So now let's go to the second equation. Oh, merde. What did I do? I want to go backwards. Ah, no, comme ça. Comme ça, okay. Ah, no. Okay, let's go now to to the second equation. To the second equation. Okay, let's go to this equation, what it means, okay? And remember, all this is in your book. All this is in your book. Okay? Should I erase, or should I stay, or should I go? Well, can I erase this?
Yes.
Can I? May I? Dugan, can I?
Yes.
Yeah, okay. Okay, let's suppose now I'm taking the commutation relationship of a generator associated with a given root with the generator associated with the mirror image of that root. Okay? So this is what this means. I have a generator E associated with the mirror image of that root with the generator E associated with the root alpha. Okay? So let's write that commutation. That commutation relation is the following. I have generator associated with a given root alpha. Do you want me to use a sub-label to emphasize that it is the J root? Do you want to use the sub-label J, or you just want me to use alpha? Do you prefer just alpha? J is good because it keeps track of how many roots do I have, okay? Of course, this is a vector. This is the root vector number J, okay? Now, associated with this root vector number J, I have the mirror image, which is the root vector minus the Viol reflection, the mirror reflection, minus J, okay? And then I'm going to take the commutator of the generators associated with the minus alpha, with the generator associated to alpha. Okay? And then that commutation relation is going to be given by a linear combination, of your Cartan basis generator. Okay? So I'm going to have Cartan basis generator number 1, Cartan basis generator number 2, and Cartan basis generator, I guess the rank of algebra was little n, right? Okay. Now I'm going to have a linear combination, so I need to know what these coefficients are. Okay? So those coefficients are nothing else but the components of your root vector associated with the root number j. Okay? So I have here, let me use it in red, yeah.
How did you write it?
Yeah, you know, he's smart. He's a smart guy, you know. Remember, your book has 2 or 3 chapters devoted to this, to the nitty mathematics of where this has to do with the secular equation. I mean, I'm only giving you the background. I mean, this is why one has to suffer sometimes and read a book. You have no choice, right? If you, yeah. So what happened? Okay. So then what I have here is, remember, I have my root number j, but of course, because I need to specify the first component of my root. Okay. Here I have to specify my second component of my root. Okay. And here I have to specify my nth component associated to my root. Okay. Nth component. Remember, this is not, I'm not taking a root to the 1 power or the root to the second power. I mean, the first component, second component, nth component. And this symbolically, what does it look now, Amrik? Now, this looks like a dot product, right? First component times the first component, plus second component times the second component, plus the nth component times the nth component. So this looks like a scalar product, right? And this is why you write it. What happened there? Did I skip? Did I jump? It jumped by itself. Okay, this is why it looks like, okay, I have to let Andre finish, yeah. It looks like a dot product, right? The dot product of my vector labeled j with my boldface h, okay? And this is what, and then of course if you use the Einstein summation convention, you have the ith component times the I component of h, okay? So this is what this equation means. So you go back to the blackboard, if you spell it out, this is what it looks, okay? So in Einstein summation convention, this will mean my vector j, I look at my ith component and I multiply with my ith component of h. Okay? So this is what this is. Okay, so let's look at the other commutators. I have my h with my h. I have with my e's commutator with the Viol reflections. Now let's look at pair roots here. Because here I'm playing with the reflection. Okay? What happens if you have a vector and if you add its opposite? What will you get? Alpha plus minus alpha? 0. Yeah. So you could think of your Cartan generators as your zero, how do you say, your zero vectors, or how do you, what word? It's not, no, how will you call it, Raymond? It's another way you can think of the Cartan generators. In other words, think of this as an eigenvalue equation. The zero eigenvalues, you can think of it as the zero eigenvalues. Anyway, the bottom line is that take alpha, if you add the argument here with minus alpha, if you add alpha, you get the 0. So you can think of the Cartan generators. The Cartan generators, you can think of them as as your, you know, as your zero, you know. Anyway, don't worry about it.
The kernel, no?
Huh?
Kernel.
The kernel, yes, the kernel. Think of it as your zero vector, quote unquote. You know, it's just a bookkeeping device. Now let's look at the, yes.
So it's all this relationship is
Yeah.
in the Cartan basis.
Oh yes, that's why it's called.
The Cartan basis.
This is how you define it. You define the Cartan basis is defined with a basis obeying all these properties.
So wasn't the Cartan basis the Cartan generators?
The Cartan, yes, the Cartan basis is the Cartan generators plus something more. Plus
All the other generators?
the Cartan basis for example, in this room it's a three-dimensional room, right? I have three fundamental bases, which is the x, y, and z. And then I'm going to look for linear combinations of those three vectors to generate the others. Okay?
No, for example,
yeah.
in the E8 case,
Yeah.
you said n plus 2j. That is the number of dimensions of the algebra,
Yes,
right?
yes.
So n, I thought, was the
Yes.
number of Cartan generators.
Yes, yes.
And hence the number of Cartan bases.
Yes,
Is
yes.
that right?
Yes, that's correct.
So then the Cartan basis is
Yeah.
nothing but the Cartan generators.
Yeah.
But
When
when you say plus,
well, we have to add.
plus is non-Cartan.
Yes. That's why you have to include the other commutation relations between the other generators with the Cartan ones. Okay.
And the Cartan ones are only the H's.
Yes, here. Okay. Yes.
So why, because the non-Cartan ones are also related to H by the third equation.
Yes. Yeah.
But the following one is not related to the Cartan.
That's right. Only when alpha plus beta equals 0. When alpha plus beta equals 0, you reproduce this guy over here. Okay? Yeah. Okay, so let's look. Okay, so the commutation relation with between a generator of the algebra associated with your root vector alpha, with a commutation relation with your root vector beta, is given by this by a superposition of generators, where now the subscript. Remember, if you have alpha here and beta here, you have this additive law. This is why it's very clever, because you label your generators in such a way that when you take the commutators, you get here a generator obtained by adding these root vectors. Okay? Because after all, you have a linear space. And your structure constants, if you want to call it, are given by these numbers here. Okay? And then I'm going to explain what, I don't know what happened here. This is strange. It's just a +1 there. The structure constant associated with this pairwise commutation relation is given by this. I'm going to tell.
Should there be a beta in there?
No, alpha. No, it's in alpha.
Only alphas.
Yes.
But alpha and beta doesn't depend on beta.
Yeah. So here, remember, you have E alpha to your left and E beta to your right. So the way it happens is that the E alpha is to your left. It describes what this value should be. Only depends on your left, the guy you put on your left.
So why did you index the n with beta?
Well, you'll see that they are related. You're going to see why they are related. You know. Well, it's because the pairwise alpha beta. This is the structure constants associated with the alpha beta commutator. Okay, just to be.
Okay, so this doesn't mean it's a function of alpha beta. It just means it's an index.
Index.
Yeah.
Yeah. Okay, and then of course, if alpha plus beta, the commutator will be 0 if the sum of this vector is not a root. Okay? And is not 0 if it's a root. Okay?
So that's n times n plus 1, right? Not n plus 1.
No, here, these are just integers. I will tell you in a minute what these integers are. Capital N is like the structure constant. And little n and little m are just integers. Okay? I will tell you what it is in a minute, what they are in a minute. Okay? Yeah.
In physics, this is very important because this is saying that one particle can interact with another particle.
Yes.
If the sum is a root.
Yes.
Not if the sum
You're
is
right.
And the result is the sum.
Yes.
So what
Is the commutator.
Yes.
So what is the sum equals root means in your
For example, a gluon and a quark.
Yeah.
So what is that? Gluon plus quark equals what? Is it a root? Is it some other particle?
Yes, it's a quark with another color.
Yeah. Yes.
If alpha is a gluon, beta is a quark,
Yeah.
then the commutator gives
Yeah.
the quark.
Yeah.
I understand the
color
commutation.
has changed, but if you want to make this with two particles where the sum of the vectors is not a root, then they cannot.
No, but what does it mean physically to say some of the
I mean physically that all the particles should belong to a representation of your Lie algebra.
Okay, so when you say alpha plus beta not equal root,
Yeah.
you're talking about two particles which will not add up to give something else? Yes?
Yeah, basically, yeah. In a pedestrian way, that's what
In
it
the
is.
root.
Yeah. Okay. Can I proceed? Can I go forward? Dagan, does this sound familiar?
For example,
The-
a particle with itself,
Yeah.
Particle with itself will
two
be
times the same particle,
Yeah.
generally the sum will not be a root.
Yeah.
An electron and an electron.
so E alpha should be zero then somewhere. I don't see that.
Yeah. Well, there's zero when the combination is not a root.
Not a root.
Okay.
It's not there.
Okay. Can I proceed? Can I? Yeah. Okay. Okay. The properties. Let's look at the properties of the capital N, the structure constant associated with the pairwise commutator of generators which are outside the Cartan basis generator. Okay. So remember, I wrote this capital N and M here. They're integers, and what are the properties of those integers? Okay. These values of N and M are determined by these conditions. Okay. Okay, so I have here just a label. Okay, and then I have the sum. Okay. Yes. Now, okay, so what is the numerical coefficient of capital N alpha beta? What happens is that out of a pair of roots, imagine you have a pair of roots. So what you're going to have is that you're going to look at linear combinations of your roots, okay? So you have alpha and beta, what can you do with them? Well, you can add them, beta plus alpha. And if you get a root, good, you're fine. Then you can actually add beta. You perform another superposition of the two roots. Alpha. And you may perform this linear superposition, and you may get another root. Then you keep adding, and you may get another root, and then eventually you will not get a root. Eventually, you see what happens is we use the n for the dimension of the rank of the algebra, and here that n is another thing. This is why we have to be careful with the notation. It's probably good to use the rank of the algebra labeled by the letter R rank of the algebra.
Okay.
It's much better. And n and m are integers, okay? And so, but eventually you will hit a point where this will not give you a root, okay?
So n is the maximum integer.
Yeah.
Like this, a root.
Exactly. So this is what I mean by n there, okay? And by m, you do the same thing, but now instead of adding, you do subtractions, okay? So you have beta minus alpha might be a root. Remember, these are the roots. I'm not talking about the simple roots here. I'm talking about the roots. The simple roots are something else, okay?
Simple roots, you can have any integer, right? Just any in your.
Yes, eventually, but well, yes.
A combination of two simple roots is not simple.
Simple. Simple roots is more subtle. The simple roots is more subtle. Eventually, you have a 2, and eventually you reach a point where beta minus m alpha is not a root. Okay, so this is what, when you reach this point, you'll be able to read what the value m is. Okay, yeah. So this is how this capital N, if you want to call it a Schrodinger constant, is defined. Okay.
It's like an allowable range.
Range, yes, yes, yes.
Yeah, we'll actually see, I don't know if you're going to talk about it, but I think I will talk about how to compute roots from Cartan matrices, and we'll see where this N and M come
Yeah.
again. Like
Later on, the Chevalier basis is even more elegant, actually.
the Chevalier.
Chevalier basis. I'll talk about later next week, which is actually more elegant. But that he came after Cartan. Okay. Essentially, the Chevalier basis is very useful because he tells you that everything you need to know about an algebra is encoded in the Cartan matrix. Okay? The Cartan matrix encodes everything once you use the Chevalier basis generator. So I'll talk about that next week. Okay, so let's look at the symmetry properties of these coefficients. So this is how they are defined, If you remember, if you reverse the order, here, if you reverse the order, you're going to change the sign, right? Because the commutators, you flip the signs. So this is why you have this relationship between alpha, beta, and beta, alpha. Okay? Then here you have another interesting relation. This is minus, minus, minus. If you have a number, if you multiply by minus 1 and by minus 1, you end up with the same thing. This is why you have this relationship here. And also here you have this relationship here is when you can flip the order beta alpha, and you have also this relationship. Here you flip beta to the left-hand side, and on the right-hand side you replace it by minus alpha plus beta is this. And here if you flip again this to the left-hand side, you get this. Okay, so these are the properties of the alpha beta. These are properties of the coefficients. Okay, this is also explained in detail in your book. Yeah. Dagan went to the restroom?
Yes.
Yeah.
Get some water.
Some water.
And it's cheese and wine.
Yeah. Do I wait for him? Shall I wait for him? Yeah. Well, I can explain to him later what. For example, okay, let's do two examples, two specific examples. Let's do the SU2 algebra, and afterwards I'll do the SU3 algebra. A specific example, so you know what I'm doing. For example, since the rank of the SU2 algebra is 1, so there's only one element of your Cartan subalgebra. In that case, you will see that that element of your Cartan subalgebra is the z component of your angular momentum. It will be, okay? And the other two elements of your Cartan subalgebra, the plus root and the minus root, they are the Viol reflections of each other, is like these ladder operators, the gxy plus y, and then the other combination. Okay, the plus is what I call plus here, and the minus. So you'll have one generator, two generators, three generators. This will be the element of my Cartan generator. Of course, it commutes with itself. And here, okay, so what do I have here? If I have an A plus with A minus, what did I put here? This plus sign. That was funny. It should be either one or the other, but not the two. I'm sorry about that. But if I take, for example, okay, let's do.
What is the typo?
Yes, yeah. No, it should be only one sign. It cannot be two signs because it's only one dimensional. Remember, the SU2 algebra has three generators. The Cartan basis is only one dimensional, so I only have a one dimensional space. Okay. So let's draw the roots of my SU2 algebra. Okay. So remember, I will only have a one-dimensional space, right? So I have only a one-dimensional space. Okay. I'm going to draw the origin of my one-dimensional space. Let's call this my origin. Okay. Yeah.
Circle, right?
This is the angular momentum. Okay. Remember I showed yesterday how the SU2 algebra was isomorphic to SO3, the double cover of SO3.
Oh,
Yeah. SU2 was the double cover of SO3. You remember yesterday? Okay. So what do I mean by
Question about that. So this is one-dimensional complex?
no one-dimensional real? Well, let's forget about the complex space. Let's say when working one-dimensional. I only have one generator, which I call it. Let's call it E1 for the moment. Let's call this the reflection E minus 1, and E sub 0, if you want to call it E sub 0. It's my Cartan element. Okay, so remember when you studied the angular momentum, when you have a Jx, you could combine it with a y to get what you call the J plus ladder operator. Remember when we studied quantum mechanics?
X is in X direction.
Yes. Y is a y direction, and my J said will be what I call my Cartan generator, which will be only one of them. Okay?
I thought SU2 has a rank 2.
No, SU2 has rank 1. Okay, remember, when you look at the table of Cartan algebras, you have this AN, rank n is associated with SLN n plus 1, or SU n plus 1. Be very careful. Be very careful. Okay? Since you are here, here, yes, here. Anyway, here you can pass this to Fang. You remember? Yeah. SUN is a tricky one. It's the first one that doesn't. Remember, rank n. So you have SUN plus 1. Okay, is this clear? Okay, so then I can have the minus combination, which is the lowering operator. This is what we could call J plus, right? Okay, so this is what I call my Cartan my generator associated with my root vector. Since I'm only dealing in one dimension, I only need to specify one number, right? Because my space is only one dimensional. A vector will have only one component. So I give this the number 1, and that's it. There are no more components to my number because it's only one dimension. So this is this point here. Okay? My J minus, I'm sorry. This is my J minus corresponds to -1, and is this here. This is my J minus, this is my J plus generator, and this is my J subset, is my Cartan generator. Okay?
Might have been useful to actually go over those
Ladder operators?
in terms of the algebra.
Yeah, I can. I'll go. If you want, we'll go back to it. But you see the picture. I have a one-dimensional space, which is this line. Okay. I have one Cartan generator, which is the Z component of my angular momentum, and I only have two roots, which is the J plus J minus.
Wait,
Yeah. I'm sorry.
I thought J was in XYZ direction. What is J plus J minus? I thought E plus E minus made sense.
No. This is what you get. You'll see why. Why? Because, okay, let's write the commutation relations of my algebra in terms of X, Y, and Z. Let's go.
So,
Yeah.
question.
Yeah.
J represents angular momentum.
Yeah.
So Jx represents angular momentum in the X direction.
Yes.
Y direction, Z
Yeah.
direction.
Yes.
J plus means angular momentum what?
In the linear combination, in this combination, in a combination of X and Y, okay, you have a linear superposition of jx with jy, and I have these two possibilities. I'm going to show you very simply. Let's write down the commutation relationship in terms of gx.
But there is a I. So this
Yeah, it's because remember, because like Duncan said, we're dealing with classification of Lie algebras. In reality, you're dealing with complex spaces. Don't worry about the. You could work actually with anti-Hermitian generators. Okay, if you work with anti-Hermitian generators, then you forget about the I. Okay? Okay? So if you work, like I say, if you work with Hermitian generator, introduce the I. If you work with anti-Hermitian generator, forget about the Y. Okay? So
Physics is listed for the EM weight, EM field, as you
the
One is here.
I be-
SU2 is electroweak, right?
Oh, yes.
SU2 is electroweak, yeah.
Electro
Electroweak, yeah. Imagine these are the W plus, the W minus, and the Z boson. Yeah. Okay. So let's write. Okay. Let's suppose I write the commutation relationships like this. You know, Jx with Jy gives me a Jz, right? Right? Yeah. Yeah. Yeah, let's write the commutation relationship of the angular momentum. Okay, let's write them, spell them out explicitly. Okay, and then okay, let's Jy with Jz. What will it do? It will be a Jx, and do I have a plus or negative sign?
So it's cyclic, right?
Let's cyclic, then it should be a plus. And when I have Jx.
So you're writing in the non-Hermitian form? Because
No, I'm writing in anti-Hermitian form.
anti-Hermitian.
Yes, yes.
So we saw it in terms of IH bar.
Yes, yes.
JH.
Here is anti-Hermitian, yeah, yeah. There are no i's on the right-hand side of the equation. So here, then I should have a Jy, and then I should have a minus, right? Because I'll have, okay. Now, what did Cartan do? Cartan did not like this representation of the commutators. He was very clever, and he said, okay, let's rewrite this commutation relationship in terms of Jx plus Jy, Jz, in terms of Jx minus Jy, Jz, and in this form. Okay, let's write the commutation relationship of this. Okay? Yeah, it's trivial, it's zero, right? But I mean, this is what it tells us that Jz, we choose Jz to be the Cartan generator.
Do you choose that?
Yes, yes.
So you can choose X if you want.
Yeah, anything you want. Yeah, you have rotational symmetry, yes, 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 yes.
Why did he not like this?
You'll see why, you'll see why. Okay, so here, what will you get when you perform this commutator? You take the Jx with Jz, it gives you what? It gives you
Minus JY.
minus Gy, d'accord. Okay? And then Jy with Jz, it gives you
JX.
Jx plus Jx. Okay? Okay, and this looks like, that. What does it look like? Jx minus Jy, it looks like J minus, right? This is J minus. Okay? And okay, let's do this guy over here. Jx with Jz, x with z, minus Jy. Okay? And Jy with the z. No, it cannot be. Minus Jy, okay, minus Jx, okay? This looks like minus J plus, right? Okay? Okay, so let's flip the order of the commutators, right? Because let's flip the order. I'm going to flip this order.
So it's going to be a negative.
I'm going to flip this order, okay? So what I'm going to have is J Z with J X plus J Y. This is what I call J plus, right? Is that it? Did I do it right? Yeah.
Gives you a J plus.
No, but
Minus G
minus J minus. Did I?
It's anti-symmetric, right?
Yeah. But if I reverse the order, I should have something which will change signs, right? So it will feel. That's strange. If it will change sign, it will give me this. But that's strange. It gives me the opposite. Anyway. Anyway, so here I have my commutator. If I choose the plus, will give me a plus. If I choose a minus, will give me a minus. Okay.
So
Yeah. So many. I'm sorry. Good. Yeah.
So that is a minus G minus. Right?
Yes.
So
So in reality, what I choose. Yeah. I beg your pardon.
it's a minus G minus.
Yeah. There is a sign. I think we screw up in.
different because we don't have the I.
Yeah. The eyes. You are right. The eyes will be crucial. Yeah, the eyes will be crucial because that will account for the signs. Yes.
No, but
Yeah,
then why did Cartan write it in that?
Yeah. Okay, so he wrote it in that form because he wanted to have J Z with a J plus to be plus J plus. He wanted to have J Z with J minus to be a minus J minus, and J Z with itself to be 0. Okay, so he wanted to write it in this form, telling you that this eigenvalue of plus 1 is associated with this root. Okay, because remember, this is what I call E1, and this is what I call E minus 1. So this plus 1 is the eigenvalue. This negative 1 is the eigenvalue. Okay? So that's why he wanted to write that way. Yeah.
Because he wants to write it.
Yes. Yes, Raymond, you were saying. Yes. Yeah. I think if you use the eyes, if you use the eyes, yeah, you get. Because of course, when you use the eyes, you're going to have. You always have those eyes when you introduce the eyes, and then when you introduce the eyes here, then the eyes will take care of the sign. I times I is minus 1, so the eyes will take care of the signs. Yeah.
So now we have the explanation of Amorit's question. What is physically Gx plus I Gy? It's nothing, but we need the I to have the things working. Because
no, because remember.
Why something?
No, because the algebra. You see, Ray wanted to have. Remember that in one of the slides, I wrote the rotation commutation relationships. Remember that I wrote them like this. Although Ray was not very happy. Remember that I wrote, for example, x sub I, x, y. Remember that I wrote with a minus sign, I, j, k, but actually Raymond was not very happy with that minus sign because he wanted to have a plus sign because of the quaternions.
That's a choice of convention.
Yeah. No, but it had to do with how you define your generators. Because remember, I can have my anti-Hermitian generator define plus I jx or minus I jx. So the choice of the signs is essential. And the signs I chose, it was with a plus I. So the commutation relations that I had an extra minus sign. Remember? Okay. So in the way I wrote them, x, y, z is an even permutation, but I chose to have this extra minus sign, remember? And then in that case, you will have that crucial sign that will take care of everything. Okay? And that's why we have this sign flip here. Okay? Okay? But this is why I prefer to use this choice with the plus I and use this convention. Okay? In that case, you'll get the right signs. Okay? So, d'accord, I don't think this is too much of a problem, you know. Just, you know, the best way to, like Raymond said, you have to always do your exercises. This is the only way one learns, you know. Okay, so I was right. I should choose that minus sign, okay, extra. Why? Is because I'm using this from your book, and Gilmore is using this convention. And that's why everything works out.
But if Raymond doesn't like it, he can absorb the minus in the epsilon, call it epsilon prime, and that fixes his problem.
Yeah. Okay. Dugan, you are thinking about something here. Yeah. Okay. So, let's look at the SU3 algebra. The SU3 algebra, remember, it has 8 generators. But remember, the rank is, Fang, now the SU3 has rank?
2.
Oh, good, now it has rank 2, exactly. All right, exactly. You cannot. Okay, so the rank of the algebra is 2, so you are going to have now. Okay, so let me erase. Before I do anything, let me just.
So what has the rank again? Can you remind me? Got to do with anything here?
With the dimension of your Cartan, the number of Cartan base.
Number of Cartan bases.
Yes. So let's try to draw the root lattice of SU3, and
Visualize the symmetry of SU2, SU3.
yeah, SU3. I'm going to draw the root diagram of SU3, and then we'll look at the commutation relationship in the Cartan basis, and then we'll. I'm sorry.
Geometrically, how
Yes.
do you understand the symmetry?
Yes, and then we'll work with the matrices and find a explicit matrix representation. So Fang agrees SU3 has rank number 2, so I'm going to have 2 Cartan generators, okay? So my space to represent my basis vector, my root vectors will be 2-dimensional, right? So I'm going to have a 2-dimensional space, okay? And I'm going to have now, this is where the simple roots come into the picture. It turns out that when you look at the SU3 algebra, or the AN algebras, they are what they call simply laced, means that all the roots will have the same length, okay? So the root lattice will be, you will have one simple root alpha, and then you'll have another simple root beta. And you only have 2 simple roots. And this angle, later we'll see, this angle will be 60 degrees. Later we'll see this. But for the time being, this is my root space. I have a 2-dimensional Euclidean space. I have 2 simple roots. Now I'm going to generate the other roots, okay? Geometrically. How do you generate the other roots? Then what you do is you take alpha plus beta will give me another root. So when you add vectors, you know, okay, I have another root here, which is given by beta times alpha, okay? So now I have 3 roots. Remember, 2 of them are simple, and the other one is a linear combination of the 2 simple roots, okay? Now what I'm going to do is I'm going to perform the Viol reflection. The Viol reflection of my roots with respect to the origin, okay? So I'm going to have this is the extra, the hexagon, yes. You have the hexagon, then you have this guy over here, and then you have this guy over there, okay? So you will have a total of 6 roots. 2 of them are simple, alpha and beta. The third one is not simple, although it's a root, because it's a linear combination of the other 2 simple roots, okay?
But
Yeah.
why is not beta plus alpha the simple?
Because
By simple roots, I mean a root that cannot be written as a linear combination of the other roots.
Other two simple roots.
Okay,
Yeah.
so it's not the positive root that you
No.
want.
Well, in this case, well, positive. This root will be in a way positive because the coefficients are positive. The reflection will be negative beta minus alpha, so this will be like the negative root because the coefficients are negative.
So
Yeah.
the simple root are not the positive root.
Simple root you have. Well, this is a simple root, but with a negative sign. This is a simple negative root, right? And this is a simple negative root. Okay, let's repeat. This is a simple positive root. Beta is a simple positive root. Minus alpha is a simple negative root. Minus beta is a simple negative root.
Okay, this
Okay.
has nothing to
No.
do with the coordinates.
No. It's only no. Okay.
But the important property is that you cannot linearly combine two simple roots to get another simple.
Yes.
Yes, right.
Yeah, that's the bottom line. Yeah. Okay, so now I have the hexagon, right? I have the hexagon, of course, and we must not forget that we also have to add the Cartan basis generators. Don't forget them. They are there. Don't forget them. Of course, they're associated with the zero root. You could think of your Cartan basis generators. You can think of them. Okay, I'll let.
So these all these 6 vectors that you
Yeah.
drew are E's,
Yes.
are the E generators.
Yes.
The
Yeah.
non-Cartan generators.
Non-Cartan.
Cartan generator
Live here. It's like the zeros.
is always the case.
Yes.
Any
Which is
algebra.
your 3 squared minus 1, right? For your number of generators. So you got 6 there and you
Yeah.
got 2 carton.
Yes.
That's
Yeah.
plus
They are not
two
the
generators.
Yes.
generators, they are the roots.
Yes. No. Okay. Like Douglas.
But the generators corresponding
But
to
each
the
root
roots.
corresponds
Yes, but they are
to
giving in the plan the
Yeah.
index of the generator.
Yeah. Let's count generators. The Cartan generators, there are 2. They are the zeros. So the zeros, the Cartan generators live here in the origin. Okay. The Cartan generators live in the origin. They are the zeros, and the other guys are the non-zeros. Okay. Okay. So let's count them. They are a total of 6 plus 2 is 8. 8 is 2 plus 6 equals 2 times twice 3 is 8, right? Because I have two copies of 3 roots. You have 1 root, 2, 3, plus the Viol reflections. The mirror image makes another SK 3, and you have the Cartan generator. 6 plus 2 is 8. Okay. Let's try this with the G2, with the exceptional Lie group G2. Okay. Let's see if I remember how to do it. But okay. So think of the Cartan generators as living in the origin of your root space.
Can it be anything?
I'm sorry?
Is the H1 and H2 here defined?
The H1, H2, who are they? Oh, I'm sorry. They are the, remember that in the yesterday I gave you the list of your Gell-Mann matrices? How many? I had 8 Gell-Mann matrices. Okay, let me show you. I guess, David, maybe we can show this here. This is important. Yeah. Let's go back to the Gell-Mann matrix generator because we can. Okay. Yeah. No. Let's remember the Gell-Mann matrices. Okay. Remember yesterday there were 8 of them. Okay. Here you have one diagonal matrix, which is lambda 3. And then we continue, and then you have another diagonal matrix, which is lambda 8. So your Cartan generators are lambda 8 and lambda 3. Okay, because you have those diagonal matrices commute with each other, and you'll have 2 of them, and those will correspond to the Cartan generators of SU.
Sometimes you have more than 2 Cartan generators.
Oh, it depends on your algebra.
Yeah.
It depends on which algebra you're talking about. Okay?
So, what are the Cartan generators, like actual matrix for SU
Well, the other ones look like this. The Cartan generator, one is this guy.
No, but this is for Gelman.
This is for SU3.
Oh, this is
Oh, that's for SU3.
Yeah, for SU2 is just 1 and minus 1, a 2 by 2 matrix.
So are these related to the 8 gluons then?
Yes, the 8 gluons. These are the 8 gluons.
So
Yeah.
it would have been so much better if they just called it the generators of SU3 rather than calling it Gelman matrices.
Gelman came in later
Yes.
because Gelman was what? He did his work in the 60s, right?
He shouldn't be. They shouldn't be known as Gelman matrices. They should be known as the generators of
Yeah.
SU3. Right?
Yeah, but Gelman used them and Gelman and Neumann used to formulate the theory of quarks.
Because these are unique, right?
Yeah, these are the physicists. You know, the Gelman matrices are nothing but the SU3 version of the Pauli SU2 spin matrices.
Yes.
It's a special
Yeah.
So for
And
each,
SU2 is the same, they don't have to have them.
Quaternions, they could have called quaternions.
Yes.
Yeah.
Really a manner of the physician to
Physicist.
compare them to object invented by mathematicians.
Yes.
100 years before.
Yeah, physicists reinvent.
Aren't they? They probably don't really know.
No, I
They
wouldn't
need
say that.
100 years to learn this.
But is this
And
the
they are
unique
still in
generators of SU3?
Well, you could have you could have other matrices that will represent the same algebra, but this is a clever matrix representation of your algebra.
This is a trivial representation matrices from the definition.
Yeah, in a way. I mean, you could choose a matrix.
Canonical, not trivial.
Canonical.
Trivial, because trivial would mean
Yeah, canonical. Yes, canonical.
how do you find the Cartan and generators for other algebras, like generally?
Well,
put on the guard of Gelman.
no, you have to. Yeah.
Get all the list of
Yes. Okay. I'm going to give you the reference. A reference by. Okay, there's a paper by a Japanese author that he posted a few months ago in the archives. Let's see, Dugan, how much pages do you think this paper is? A Japanese guy posted a paper in the archives that deals with all these questions that Fang is asking.
You want me to guess how many pages?
Yes, let's see how many pages do you think this paper is?
127.
Okay, Fang, how many pages do you think this paper is?
30.
Yeah.
I'm going to say 2.
Okay. I'm sorry?
2 pages.
2 pages.
Trick question.
Yeah.
95.
Yes, you, Ray.
248.
He did not write the paper.
Yeah. David, any guess how long this paper is in the archives? How many?
1,200 pages.
Yeah. This paper is almost 1,900 pages long.
19,
Yes. How many tables do you think he has in this paper?
hundreds?
One every other page.
Yeah, he has about 900 tables.
You're pretty close. You know,
Yeah, he's an artist.
order of magnitude, correct?
He's an artist.
Read it in Japanese.
Remember, he's an artist, and they have a lot of intuition. Yeah. So I will give you the reference. This Japanese author gives you all these ways. How many ways can I construct grand unification models in 4 and 5 dimensions using the table of all the known Lie algebras? So you have thousands and thousands of grand unification models, including E8, E7, okay? And then the first 100 pages, Fang, in the first 100 pages, he tells you how to do this.